Hypothalamus Artificial Intelligence, High Presence. Industry 6.0. Artificial Business Management. Conference for managers and executives who want to know the future of artificial business management. Artificial Business Management. A new way of looking at business management, which will change the world as we know it. In 2023, result of the Industry 4.0 revolution, artificial intelligence robot Mika was the leader of the luxury liquor company, Dictator, based in Poland. Dictator has signed a contract with Mika, who now sits on its board of directors and holds the position of CEO. Enterprise-wide optimization will be the methodological approach of the artificial hypothalamus of the cognitive robots that run companies. That is the future that awaits us. Artificial business management refers to the integration of artificial intelligence, AI, and mathematical modeling technologies into an organization's core processes, to optimize decision-making, automate operations, and personalize the customer experience. Unlike traditional methods based on human judgment and static historical data, this model uses predictive and prescriptive analytics, and real-time monitoring to improve the accuracy of results. To help overcome the COVID-19 pandemic, AI researchers around the world responded quickly to find ways to use AI algorithms. Applications were developed in the following key areas: forecasting, diagnosis, containment and monitoring, drug development and treatment, and medical and social management. Some, such as forecasting, aim to predict new outbreaks to aid policymaking, while others focused on reducing the impact on health services through remote triage. This impact on humanity changed the artificial business management in developed countries and accelerated the development of autonomous systems. Enterprise-wide optimization systems. High, thanks to its peculiar vision of mathematical modeling, which is not based on computer programs, but on a relational database, which is used by a generative artificial intelligence that interprets the database, and produces all the necessary computational code, can quickly implement what Professor Jeremy Shapiro called enterprise-wide optimization. In line with High's vision, enterprise-wide optimization systems are the evolution of traditional decision support systems, which have accumulated several mathematical models, many of them without following a standard, which ensures consistency across all models. These models run independently of each other, and are usually coordinated by a database, or multiple databases, that integrate the input-output. While each model can ensure optimality, this approach is not optimal, as there is no company-wide model. High first heard about AWO in the article Beyond Supply Chain Optimization to Enterprise Optimization, written by MIT professor Jeremy Shapiro, in which he states, AWO arises from the recognition that strategic supply chain planning needs to be integrated into broader business planning exercises, so that it serves to break down artificially created barriers to fact-based decision-making. According to Shapiro, the growing interest in supply chain management is the result of two overlapping motivations. Managers are looking for business models and processes that support fact-based decision-making for the design and operation of their supply chains. Fact-based decision-making refers to the development, validation, and application of data-driven mathematical models to analyze real-world business planning problems. Managers seek to integrate decisions across supply chain functions, in geographically dispersed facilities, and over time. The essence of fact-based supply chain management is integrated planning. AWO is based on applied mathematics and the great development of information technologies. AWO arises from the recognition that strategic supply chain planning needs to be integrated into broader business planning exercises, so that it serves to break down artificially created barriers to fact-based decision-making. According to Shapiro, the growing interest in supply chain management is the result of two overlapping motivations. First, managers are looking for business models and processes that support fact-based decision-making for the design and operation of their supply chains. Fact-based decision-making refers to the development, validation, and application of data-driven mathematical models to analyze business planning problems in the real world, which involves close relationships between all functions of companies. Second, managers seek to integrate decisions across supply chain functions, across geographically dispersed facilities, multiple businesses, and over time. The essence of fact-based supply chain management is integrated planning. The diagram clarifies the concept. The marketing and sales manager, MANV, presents a budget for advertising, promotion, pricing, and sales force activities for the planning horizon. The marketing science model calculates sales for each period. It should be assumed that sales will equal demand, as it is a waste of marketing expenses to generate unmet demand. The model calculates net marketing revenue, which is equal to the gross revenue received from sales minus marketing costs. This will be MANV's contribution to the company's revenue. The marketing department is responsible for setting the price and sales volume pairs and selecting the most convenient. It's a typical revenue management problem, and it's not the responsibility of the supply chain department. Many MANV managers are uncomfortable with quantitative methods, which in this case involve statistical estimation of elasticities, and price optimization. Although the scientific marketing literature describing these methods is extensive, the reluctance of managers in many companies to use them remains high. A simple demand forecasting model is not an AWO solution. High models mainly support two types of industrial planning activities. S&OP, sales and operations planning activities that are carried out periodically, usually every month or every week, to coordinate the selling products with production activities. IBP, integrated business planning, activities that are carried out periodically, usually every 6 months or every year, and aim to perform integrated value chain of the organization planning. In 2006, Jeremy Shapiro published the article Beyond Supply Chain Optimization to Enterprise Optimization, in which he stated, "The recognition that strategic supply chain planning should be integrated into larger business planning exercises will serve to break down barriers to fact-based decision-making. Starting from SCM or supply chain management, focused on production, as a first step in standardized planning." Shapiro envisions what the S&OP, sales and operations planning model, formally is, as the integration of sales and production planning. And finally, he establishes what is now IBP, integrated business planning model, which involves the financial planning as enterprise planning. That implies the incorporation of ALM models, assets and liabilities management, as part of supply chain planning. Until the advent of Industry 4.0, S&OP modeling was concentrated on production modeling. Considering as parameters exogenous, the result of models for sales and maintenance. The financial results are obtained from a post-processing, in some cases in Excel books. In the ERA of Industry 4.0, S&OP may be constructed based on 8 groups of solutions or systems: production, energy, maintenance, distribution, sourcing, human resources, financial, and sales and marketing. I view the systems as groups of equations that must be included in the S&OP mathematical problem depends on many factors. Since the equations are defined in a database, the configuration of a problem is limited to selecting from the equation store, which are the ones that the modeler wants to consider in the model. Visually, it is easy to see the evolution of the traditional S&OP concept to a modern IBP, that covers, virtually, all the operational functions of an industrial organization. This leads to two problems that must be solved from a computational point of view. If traditional approaches are used, a large number of programmers are required to generate all the necessary source code, and to coordinate all the models, and large computational power is necessary to solve the integrated problem. Digital industrial revolutions. Today, the evolution of industrial revolutions is conceived as Industry 6.0 is completely changing the mathematical modeling of artificial intelligence. Now we can talk about orchestration of swarms of cognitive robots, and living industrial ecosystems. These two terms are new to most people, including scientists, even though they date back at least 15 years. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are: integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are: mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university, however, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. Now GPT is the intelligent, and super-fast, consultation of what is recorded on the internet, which limits many professionals to this knowledge. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. Human intelligence and artificial intelligence. As the name implies, artificial intelligence is the result of the scientific effort to provide intelligence to machines, to replace the systematic processes carried out by humans. Today, artificial intelligence takes the form of high-speed mathematical algorithms, implemented in the different types of computers available. And it's the result of modeling human intelligence from biological neural networks, which are a fundamental part of our brains. But there's no denying that this view of intelligence is limited, as it only looks at one element of the human brain. Recently, innovative scientists, like Jeff Hawkins, have begun to look at artificial intelligence from a new point of view, integrating the structure of the cerebral cortex into previous knowledge developed for neural network. Based on Hawkins' studies, and High's experience, Jesus Velasquez Bermudez, CSO of High, began in 2017 the process of integrating a coherent theory to unite the concepts of neural networks, with large-scale optimization, and with structured mathematical modeling. To this end, neuroscience studies and the structure of the human brain have been reviewed. The result is a coherent theory for the implementation of artificial brains for companies, following the modeling principles of enterprise-wide optimization. This gives rise to a new vision of artificial intelligence, which High has called decision-making artificial intelligence, which will support artificial business management. Human intelligence has evolved along with human beings. From an incipient basic intelligence, in the origins of human beings, that needed to see to believe, to a highly developed intelligence, with intuitive scientific ability, which can mathematically predict the behavior of the universe, without having to perform verification experiments. This is the case of Einstein, who, after experimentally demonstrating the theory of relativity, developed multiple theories that history was responsible for demonstrating. To understand this process, High describes human intelligence as composed of three intelligences. Mental intelligence, basic to all human beings, oriented to the recognition of patterns, without an understanding of why it identifies them. Mathematical intelligence, which is developed by trying to understand why these patterns occur, to explain behavior in the real world. It's not innate, it requires math, starting with algebra, all the way up to parallel math, which today's big computers require. It focuses on scientific decision-making. Many humans never develop it. Creative intelligence. It is developed by privileged human beings, who learn to use mathematics to create the theories that are required for the humans to move their mathematical intelligence. Very few humans develop it. Human knowledge, mental intelligence. Human knowledge is supported by three types of intelligences. Mental intelligence, it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence, which exists and develops in all humans. Mental intelligence and pattern recognition. Mental model is oriented to identify patterns, its foundations are not mathematical, and respond to data processing, and evaluation of eventual, and systematic, experiences. It is based on good practices. Pattern recognition is a data analysis method that uses machine artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds, or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that most performs the human being, for example identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, and etc. All this with the aim of establishing the conditions of the environment, in the past, the present, and the future, and based on this knowledge make decisions. How the brain identifies patterns is not properly known, but it is mimicked by traditional artificial intelligence. Then, the starting point of the name of artificial intelligence is associated to the pattern recognition. Today, the association is direct, and it seems that artificial intelligence is reduced to this function of the human brain, what has concentrated great amount of scientific research in working in this direction, forgetting other human brain functions. It seems that artificial intelligence is reduced to the emulation of mental intelligence, whose function is little known and explained. That is why it is known by scientists that neural networks can predict how a system will behave, but that in general the parameters found cannot be explained, they have no clear content, just as the humans cannot explain how this function works in the human brain. But this approach cannot be said to have been unsuccessful, as it effectively and massively replaces activities that ordinary humans did not think machines could perform. At first, neural networks were aimed at finding ways of connectivity of artificial neurons, seeking to improve the results of prediction. Something like a statistical model in which many algebraic models are tested, until a good solution is found. Little has evolved to try to explain content in this connectivity. This is the case with GPT. The essence of the so-called artificial intelligence is mental intelligence represented from the study of biological neurons. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. As the diagram presents it, a neural network is an interconnected group of nodes that allows computers to recognize patterns in data. This area of science corresponds to predictive analytics. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets, specialized in performing specific pattern recognition. For this, the basic patterns of ANNs are modified. Artificial neural network modeling has evolved to the point where networks with specialized structures can perform specialized functions. Convolutional artificial neural nets. They correspond to ANNs specialized in identifying certain types of patterns, such as images. The image presents an example of an ANN oriented to recognize images of numbers written freehand. The result is a discrete indicator associated to the number read. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows him to perform the analyses to understand and discover the models that govern the universe that is written in the language of mathematics, Galileo Galilei. We will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic of humanity. In practice, very few humans have this ability, and discipline. For the convenience of the reader, decision-making artificial intelligence, DMAI, will be presented in comparison to traditional artificial intelligence. The first big difference is that DMAI is based on the study of mathematical intelligence, which focuses on the representation of the physical world through algebraic formulas, or through differential calculus, and solves problems using exact mathematical algorithms, aimed at finding the best decisions. This area of science corresponds to prescriptive analytics. The essence of mathematical intelligence modeling is based on the study of the human brain, based on neuroscientific studies. The result is the production of artificial brains. From human brains to artificial brains. The image shows a Close-up of the human brain showing the activation of neurons and neuronal extensions of the limbic system, mammillary pituitary gland, amygdala, thalamus, cingulate gyrus, corpus callosum, hypothalamus. This indicates that the human brain is composed of groups of neurons which in turn are composed of groups of lower-level neurons, or individual basic neurons, called by Hi the atoms of the system. The central idea of the artificial brain is to build an artificial intelligence that mimics the human brain, leaving aside the approach of trying to represent the entire brain using a single network of artificial neurons. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. The components of the human brain have at least two levels. On the first level, there are the main organs such as the neocortex, the hypothalamus, and the hippocampus, and on a second level, the neurons that make the main organs. The image shows on the left, the motor neuron of the spinal cord, on the center, the neurons of the pyramidal cell of the hippocampus, and on the right, the neurons of the pyramidal cell of the cerebral cortex. The living industrial ecosystems is how large brain systems operate, such as the neocortex, the hypothalamus, and the hippocampus, and the orchestration of swarms of cognitive robots. It is the way in which the thousands of neurons operate within these systems. Velasquez, in 2021, published on SSRN, the paper Artificial Hypothalamus, Artificial Intelligence and Mathematical Programming Integration, in which the foundations of artificial brains, and more specifically of the hypothalamus, are laid. The article, and others later, carefully studies the relationships between the structures of the neocortex, with those formed when a mathematical problem is atomized, to use large-scale optimization methodologies, oriented to the partitioning and decomposition of systems, and they define the artificial brain in semi-detail. This is a disruptive vision of artificial intelligence, considering the power of computers, the evolution of mathematics, and the Internet of Things. This conference explains in a summarized way this evolution, based on the current state of AI. A complementary document is Artificial Brains, Augmented Artificial Intelligence, Artificial Neocortex plus Artificial Hypothalamus plus Artificial Hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus, where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. The operation of the artificial hippocampus is presented as an expert system that must store two types of knowledge: formulation, the components of mathematical models, and historical data of the results generated solving the mathematical problems. Using large-scale optimization methodologies, this information is used as starting point in future uses of mathematical models to support decision-making. The neocortex contains millions of neurons that communicate with each other to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. Sparse artificial intelligence is the Hawkins network model. Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. Hawkins is an American businessman, neuroscientist and engineer. He co-founded Palm Computing, where he co-created the Palm Pilot and Treo, and Handspring. He subsequently turned to work on neuroscience, founding the Redwood Center for Theoretical Neuroscience in 2002. In 2005 he founded Numenta Incorporated, where he leads a team in efforts to reverse engineer the neocortex, and enable machine intelligence technology based on brain theory. He is the co-author of On Intelligence, 2004, which explains his memory prediction framework theory of the brain, and he is the author of 8,000 Brains, A New Theory of Intelligence, 2021, based on his research in neuroscience. As a result of his studies, Hawkins proposes the hierarchical temporal memory, HTM neuron, that is a biologically constrained machine intelligence technology, and the sparse artificial intelligence model. This section is based on the paper Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World. Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. In mathematical models, it is common to use a matrix that relates columns with variables and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. Sparse artificial intelligence. The Hawkins network model introduces a new feature in cortical columns that proposes that a representation of location calculated within the subgranular layers of each column. The representation of location is relative to the object being sensed. Pairing sensory features with locations is a requirement for modeling objects and therefore must occur somewhere in the neocortex. Hawkins proposes it occurs in every column in every region. The network model contains 2 layers and 1 or more columns. Simulations show that small single-column networks can learn to recognize hundreds of complex multidimensional objects. Given the ubiquity of columnar and laminar connectivity patterns, the columns and regions have more powerful recognition and modeling capabilities than previously assumed. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. In summary, the modeling of the structure of neocortical regions is organized into columns and layers. Connections between layers run mostly perpendicular to the surface, suggesting a columnar functional organization. Some layers have long-range lateral connections suggesting interactions between columns. Similar patterns of connectivity exist in all regions, but their exact role remain a mystery. All regions have a motor output. Hierarchical temporal memory, HTM, is a biologically constrained machine intelligence technology developed by Numenta. Hawkins' work gives rise to the HTM neuron, that is intended to emulate the overall structural and functionality of the human neocortex. The main properties of HTM is hierarchical structure, sparsity and modularity. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model to process it in parallel. Large-scale optimization and swarms of cognitive robots. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The solution of an optimization problem using large-scale methodologies is based on partitioning the problem into two subproblems that must be solved in coordination. It can be said that there are two basic methodologies that bring together majority of applications: Bender's partition theory, BT, and Lagrangian relaxation, LR. They can be considered complementary. In BT, the partition is performed according to the variable's type. It is a primal method that works on primal feasible zone. In LR, the partition is performed according to the constraints type. It is a dual method that works on dual feasible zone. The hierarchical structures produced by large-scale methodologies do not simply correspond to mathematical artifices to solve large-scale problems. These structures are linked to representations of reality. To model a real system, two visions are possible. Top-down implies a monolithic vision, based on sequential synchronous mathematics. From the bottom up, a parallel atomized vision, based on parallel asynchronous mathematics, oriented to large-scale optimization methodologies. This hierarchical approach can be changed by the vision of an artificial hypothalamus, in which the problems work cooperatively, and have a protocol of communications between them, to solve a common problem, running in parallel. The mathematics to solve these multi-problem parallel processes are already developed and proven. The large-scale methodologies allows to divide a monolithic problem into multiple problems that can communicate to each other. Partitioning and decomposition divides the problem into multiple subproblems, represented in the diagrams by colored submatrices, which link them to subproblems. Depending on its complexity, the ways to divide a system may be non-numerable. In the image, the green diagram corresponds to the matrix, and the blue diagram to the associated hierarchical structure. The diagram shows a two-level structure. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. In 1983, Tony Van Roy created the cross-decomposition approach, to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. Large-scale mathematical model structure. From the point of view of multilayer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. Human knowledge, analytical intelligence, or creative intelligence. To develop creative intelligence, it is necessary to understand the lives of creative scientists and their way of working, then it will be possible to try to model that process. Prior to the birth of computers, the scientist's routine could be summarized in iterative processing based on formulation of a creative idea attached to a theory, conducting experiments with the aim of validating the theory or finding errors to reject or to adjust the theory. If the experiments validate the theory, the creative process is over. Otherwise, the theory is adjusted, and new experiments are carried out. This process can be slow, due to the time consumed in each experiment, which can include setting up the experiment environment, which could involve complex processes, mainly when a laboratory with ideal conditions must be built. To develop creative intelligence, it is necessary to understand the lives of creative scientists and their way of working, then it will be possible to try to model that process. Prior to the birth of computers, the scientist's routine could be summarized in iterative processing based on formulation of a creative idea attached to a theory, conducting experiments with the aim of validating the theory or finding errors to reject or to adjust the theory. If the experiments validate the theory, the creative process is over. Otherwise, the theory is adjusted, and new experiments are carried out. This process can be slow, due to the time consumed in each experiment, which can include setting up the experiment environment, which could involve complex processes, mainly when a laboratory with ideal conditions must be built. Scientific thought. A scientist thinks critically, questioning the established and using the scientific method to systematically investigate the world, seeking explanations based on observation, experimentation, evidence, and logical reasoning. This way of thinking is characterized by curiosity, skepticism toward unfounded conclusions, openness to new evidence, and collaboration with others to generate verifiable knowledge not accepted by mere authority or common thinking. A scientist is characterized by the ability to ask questions about the why of phenomena and seek answers, which drives research, based on the systematic collection of data through observation and conducting experiments to test their interpretations of reality. Scientific conclusions must be supported by verifiable evidence and objective data that others can verify. He uses logic to associate concepts, generate new ideas and order knowledge into coherent theories. The scientific method is a systematic and objective process for acquiring new knowledge, which consists of observing a phenomenon, formulating a hypothesis, designing and conducting experiments to test it, analyzing the data, and finally reaching a conclusion. The main characteristics of this method are the falsifiability and reproducibility of the results, which allows other scientists to verify the findings and expand knowledge. The phases of the scientific method include observation, research, experimentation, and data analysis. The most important action is the formulation of hypotheses by finding a tentative assumption or explanation for the observed phenomenon. The conclusion of each step will be to determine whether the hypothesis is valid or not, based on the analysis of the data. If the hypothesis fails the test, the hypothesis must be changed, which involves change the basic theory. This means changing the mathematical model that explains the process, or change or increase experiments. During the 4.0 revolution, Hai considered it impossible to emulate creative intelligence. However, the evolution made during the 6.0 revolution has made possible to model the scientific thought process, thanks to the computational power available to scientists. The proof of this is the speed with which we produce knowledge. It took many centuries, perhaps hundreds or thousands, to produce algebra, but knowledge is produced faster every day and expands its frontiers. With the appearance of the digital computer in 1947, a new science has been created, mathematics for computing, new algorithms that allow problems to be solved using a technology totally different from that of the past. The solution of scientific problems on paper has already disappeared. When the previous trend changes and the era of creative artificial intelligence begin, it is possible for humanity to reach a singularity. Real case, protein design. A protein chain, or polypeptide chain, is basically a succession of amino acids linked together like the links in a necklace. Protein design is the process of creating sequences of amino acids, which fold into specific structures to fulfill a certain function, such as curing diseases or creating new materials. 10 years ago, between 2014 and 2016, protein design was a significantly slower and more expensive process than today, based on physical simulation and fragment assembly. Today, the use of artificial intelligence has drastically reduced protein design time, transforming processes that previously required months or years of laboratory experimentation in just seconds or minutes. According to the Nobel Committee, David Baker, Demis Hassabis and John Jumper won the Nobel Prize in 2024, because they developed an artificial intelligence model to solve a 50-year-old problem, predicting the complex structures of proteins, in just seconds or minutes. From now on, competitive scientists must be advanced users of creative artificial intelligence. In general terms, the model of the scientific method is formed by a theory, a mathematical model represented by equations and by parameters that determine the experiments to be performed. The implementation of a creative intelligence, which produces an artificial general intelligence, involves the mathematical model of the scientific method to process it into mathematical intelligence. If the hypothesis does not pass the test, the hypothesis must be changed. That implies changing the basic theory. This means change the mathematical model that explains the process, or change or increase the experiments. This iterative process ends when some condition of time, precision or feasibility is met, that is, when the hypotheses are satisfied. Depending on the computational power, the number of experiments that can be performed is not countable. Depending on the modeler's skill, the model can adjust the theory, and perform the corresponding experiments. This is a creative artificial intelligence. Human knowledge, mathematical intelligence. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. This ability to understand mathematics, and to handle it, does not extend to all humans. It is necessary to acquire knowledge and experience, to handle this intelligence properly. At present, its development is directly related to the ability to handle computational and mathematical technologies. Mathematical intelligence and decision-making. Decision-making process is the final objective of any person or organization, which seeks to make the best decisions from its point of view, its criterion. This process, when carried out in real time, requires a great capacity for mathematical calculation, to handle the complexity of the real world, which increases over time, since the universe increases its entropy at each moment. When humanity began its evolution, it only had mental models to support its decisions, which seriously limited the speed of the evolution of the species, due to the little, almost zero, capacity of mental models, which led the human being to make decisions with very few calculations, or without them. Thanks to analytical intelligence, human beings developed their mathematical intelligence, which has led us to Industry 4.0. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. Lagrange's work is absolutely sound, based on formal mathematical laws, and not based on the observation of mental models of special smart animals. But their knowledge involves formal, and not just superficial, study. To think that a real-world problem can be solved better by a metaheuristic, faster, more precisely, and closer to the optimum, than an exact method, is utopian. Although in its beginnings traditional artificial intelligence did not look at neuroscientific studies as a fundamental support, there are currently clear trends of recognized researchers, who consider that neuroscientific studies should be the basis for understanding the functioning of neural networks in the brain. Two of these researchers are Geoffrey Everest Hinton is a British-Canadian cognitive psychologist, and computer scientist, most noted for his work on artificial neural networks. Hinton is considered as a godfather of artificial intelligence, having championed machine learning decades before it became mainstream. Recently, in a CBS chatbot, Hinton said that for several decades, he has been more interested in understanding the functioning of the brain than in building artificial intelligence algorithms. One of the most famous neuroscientists, Santiago Ramón y Cajal, was a Spanish physician and scientist, specializing in histology and pathological anatomy. He shared the Nobel Prize in Medicine in 1906 with Camillo Golgi, in recognition of his work on the structure of the nervous system. Through his investigations into the mechanisms governing the morphology and connective processes of nerve cells, he developed a revolutionary new theory that came to be called the neuron doctrine, since brain tissue is composed of individual cells. Humanist, as well as scientist, he is considered the head of the so-called generation of sages. He is frequently cited as the father of neuroscience. While humans in prehistoric times did not have access to mathematical intelligence, because they were creating it, today it is the engine of human knowledge, and ideally should be handled by all humans. Unfortunately, this is not the case. Therefore, its management must be part of the artificial intelligence that humanity is creating. The same thing happens with creative intelligence, the knowledge created by scientists, and the way to produce it is part of today's human intelligence. Monolithic mathematical models. With the advent of the digital computer, in 1947, computer-oriented mathematics, and the first digital mathematical models were born. These models, due to the initial limitations of computers, were thought monolithically to be solved in computers with a single processor. This quickly exhausted the dimension of problems that could be solved. Atomized mathematical models. At the beginning of the decade of the 60s of the last century, the researchers presented the first works aimed at dividing the monolithic models, to convert them into modular, atomized, models. In the opinion of the speaker, this effort was made to get models more manageable, which resulted in lower memory requirement, and faster solution of mathematical problems. At that time, there was no parallel computing. Parallel computing. The evolution of computers, from the single-processor computer, to the multiprocessor multi-core computer, opened the way to large-scale methodologies towards parallelism, since the mathematical bases were already implicit in all the works of Danzig, Wolff, and Benders. Today, they become fundamental methodologies, since the computers that are most used are multi-CPU and multi-core. Additionally, connectivity between computers turns the limits of parallelism into an infinite number of possibilities. This gives the opportunity to the birth of artificial brains. When formal mathematical models of real systems are known, the inability to use them, in human everyday life, is directly related to the very low speed of mathematical calculation that humans have, which does not allow the scientist to solve in real time the mathematical problem associated with the knowledge that he has. For robots, computer technology has overcome this inability, allowing them to solve in real time increasingly complex real problems. Only when humans will be able to bring the mathematical calculation power to the human brain, we can use the known mathematical models in human everyday life. However, organizations can already build their own artificial hypothalamus, using existing computational power. The power of artificial intelligence that we can use depends on the support network in the cloud, the local PC that serves as the user interface, and the power of the algorithms that are in the cloud and in the PC. If you want to implement powerful AI, you need to understand informatic, algorithms, and computer programming. The success is directly related to the ability to implement first and second level algorithms. Nowadays, the computer system is very complex and is part of the success. For example, Geoffrey Hinton, in the CBS chatbot referred previously, indicated that if, in 1986, he had tried to solve the problems that we can solve today, he believed that the computer used in 1986 would not have solved the problem yet. A small example of the power of computation is the case of regression models, which comes from genetics and was popularized by Sir Francis Galton in the late 19th century, with the publication of Regression Towards Mediocrity and Hereditary Stature. Today it is one of the fundamental techniques of predictive AI, parameter identification, but its concepts and limitations have not changed. They are: the number of observations must be greater than the number of parameters to be adjusted. The greater the number of parameters, the better models are generated in terms of goodness of fit, and if the number of observations is greater than the parameters, there will be redundant observations, which if used in the regression will produce confusion in the results to be obtained. In the origins of computing, the problem was the observation storage capacity, the power required to execute the process, that depending on the methodology, requires the inversion of a matrix of the size of the observations. With these constraints, estimating a model of thousands of parameters was a challenge. With the progress of computation, also evolved methodologies, estimation algorithms, until today to the conjunction of computing power and algorithmic power, which gives direction to the effective application of GPT models, which in practice permanently estimate models of hundreds of thousands, or millions of parameters. In the same way, will grow the power of prescriptive AI. If large-scale multi-level optimization methodologies, based on the partitioning and decomposition of systems, are applied to obtain the smallest atom of a dynamic stochastic model, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms, working autonomously and permanently, to achieve the goal proposed by the decision maker. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. Industry 6.0 Algorithm Swarm. The evolution of the algorithm swarm during Industry 6.0 has been very extensive, since from coordinated swarms they have become swarms of autonomous and independent cognitive robots. To visualize the difference between the information provided by a monolithic model and an atomized model, we can think of a medical examination based on a photograph, and one based on an X-ray. Photography does not allow us to understand what is happening inside the human body, X-ray does. That is an advantage that cannot be achieved with a monolithic vision, which only provides aggregated information. Atomization allows to understand how a system is assembled, and how information flows inside. The evolution of swarms of cognitive robots can be interpreted as the evolution of X-ray technology. All the developments, in mathematics applied to solving real-life problems, converge to parallel processing and the large-scale mathematical programming. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous, real-time distributed optimization. To handle the concept of mathematical intelligence, Hai developed the concepts of mathematical artificial neural nets, MANN, which complement the concepts of artificial neural networks, ANN. Those interested in the topic can watch the video. The future, mathematical artificial neural nets. Hai developed the mathematical artificial neural networks for the orchestration of swarms of cognitive robots that allow simulating decision-making in artificial brains. This is typical of Industry 6.0. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture, and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for conda, text digesting, content generation, and search bots. GPT is the state-of-the-art of the standard artificial intelligence. ChatGPT, produced by OpenAI, is the state-of-the-art commercial artificial intelligence GPT. Is ChatGPT a neural network? Yes, it is. ChatGPT is a natural language processing model that uses a neural network to power its understanding and conversational responses to users' text prompts. Specifically, ChatGPT works with a large language model, LLM, called GPT-3, developed by OpenAI and which has 175,000 million parameters. This is due to the current computational power and the great availability of data on the web. ChatGPT uses a feed-forward neural network as well as a normalization layer to generate its human-like responses. The feed-forward neural network applies a nonlinear transformation to the input stream, ensuring that the model can learn complex patterns in each dataset. The normalization layer stabilizes this training process by making sure that the input values have a relative scale size. It uses a machine learning technique, called fine-tuning, to ensure it responds to prompts accurately. However, it should be noted that, like any predictive method, it meets certain basic characteristics. You can set the accuracy of what you predict for the sample. In a regression process, this precision is called R-squared. As the number of parameters increases, the accuracy increases. But too many parameters lead to problems of overestimation. Accuracy depends on the quality of the sample, it can never explain what is not in the sample. But their ability to solve real decision-making problems, different from advanced pattern recognition, is minimal, if not nil. For many data scientists, data-oriented models are the only artificial intelligence out there. This includes academic teaching. This entails a problem of development of artificial intelligence, since many executives and managers not experts in AI, think that the only artificial intelligence that exists is predictive. Then, it is applications such as ChatGPT, and the like, that will be considered the AI of the future. Massification of ideas. A lot of ideas go into GPT, comes out one. GPT drives cognitive synthesis and the trend toward homogenization that occurs when using large-scale language models. In artificial intelligence, the synthesis funnel is the phenomenon in which many ideas enter and only one comes out. This is due to the architecture of GPT models. The process can be described as data compression. During its training, the model processes trillions of text fragments, ideas, facts, styles, and converts them into mathematical vectors or embeddings. Statistical prediction. Instead of choosing the right idea, the model calculates the answer with the highest statistical probability, based on the patterns it has learned, acting as a filter that discards the less common options in favor of majority statistical consensus. With this approach, creating a new idea is impossible. Noise removal. The synthesis process helps to control fragmented information, transforming disordered data into a coherent and structured narrative, but unique. Massification has critical side effects on diversity of thought and knowledge. Homogenization of thought. By favoring the most frequent patterns, AI tends to produce average or generic content, which dilutes individual creativity and minority voices. Creative illusion. Studies suggest that although GPT generates ideas quickly, most can be repetitive or similar, lacking the diversity that human critical thinking brings. Confirmation bias. The model is optimized to give answers that are satisfactory to the user, often leading to constant self-validation rather than challenging ideas with conflicting perspectives. GPT forgets that, for Henrik Ibsen, in scientific thought the majority is never right. The phrase "the majority is never right" is a famous statement, by playwright Henrik Ibsen, who argues that the dominant opinion often prioritizes comfort, conformity or popularity over objective truth. Ibsen asserts that conventional wisdom, or popular consensus, is often flawed and that progress comes from minority and independent perspectives. He argued that an enemy of humanity is the majority, which is made up of ignorant people, who cling to social lies, suggesting that they take a long time to be right, if ever. The phrase "the majority is never right" is a famous statement, by playwright Henrik Ibsen, who argues that the dominant opinion often prioritizes comfort, conformity or popularity over objective truth. Ibsen asserts that conventional wisdom, or popular consensus, is often flawed and that progress comes from minority and independent perspectives. He argued that an enemy of humanity is the majority, which is made up of ignorant people, who cling to social lies, suggesting that they take a long time to be right, if ever. Mark Twain said, "Whenever you're on the side of the majority, it's time to pause and reflect." Artificial hippocampus. Storing mathematical components. OpTex, HI's artificial intelligence to develop artificial brains, manages the artificial hippocampus. It is oriented to make high-complexity large-scale mathematical models without programming. The models are built in a modular way, as if they were a Lego set, which are formed by a compatible system of equations, the Leo parts, for all models. When considering that an artificial brain will gather, in an integrated way, the mathematical models required by an organization, we must be aware that a traditional approach, based on programmers, is a very difficult path, if not impossible. As everything has evolved, HI has developed OpTex, the artificial intelligence to produce artificial intelligence algorithms. The development of artificial intelligence for decision-making at HI is based on the praxis of intensive prescriptive analytics. HI developed OpTex, Optimization Expert System, a multi-model optimization artificial intelligence tool, which complies with the principles of an artificial hypothalamus, and the development of methodologies that can be coupled to multi-level mathematical structures, such as those of the artificial cortex, and source code generation, to eliminate manual computer programming tasks. Two different worlds. Without fear of being wrong, it can be said that as people and organizations walk the path from arithmetic to Industry 6.0, an abyss is generated, which materializes in the speed with which society produces knowledge and wealth, using advanced artificial intelligence. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.